For unit vectors, they have many applications, and it's really useful to find a unit vector that has the same direction as another vector, as a non-zero vector. So to do this, what we're going to do is just divide by its magnitude or its length. Remember, to get magnitude, we're using the distance formula, but if it's in standard position, if it starts at the origin, it's very simple. It's just going to be our magnitude, it's just the square root of the two components squared. So if you want to call it a and b, or x and y, whatever you want to call it, x squared plus y squared. Okay. So we're going to use this formula where we are just dividing by that magnitude. So what we want to know is that u is a scalar multiple of v, and that it's going to have the same direction but a magnitude of 1, hence the name unit vector. That just means one unit, just like unit circle. So to find a unit vector in the direction of v is negative 2, 5, what we want to do is to first find its magnitude of v. So the magnitude of v is going to be the square root of negative 2 squared plus 5 squared. So that's the square root of 4 plus 25, or the square root of 29. Okay, so now we need to use this formula. So our unit vector, and it's supposed to be bold, but we're handwriting, so close enough, is going to be the vector, so negative 2, 5, divided by the magnitude, which is the square root of 29. Remember, that's really a scalar, so we can think of this as 1 over root 29 times the, vector negative 2, 5. Okay. So we could rationalize this if you want. It doesn't make a difference if we do it now or later. That's going to give us negative 2 over root 29, comma, 5 over root 29, or if we rationalize it, which might have been easier to do from the beginning, that's negative 2 root 29 over 29, comma, 5 root 29 over 29. All right, so what we want to do from here is just prove that it's going to have a magnitude of 1. So we want to find the magnitude of u now. Okay, and it doesn't matter which we're going to use. I'm going to go back to this one before we rationalize, just to make life a little bit easier. And we want to take the square root of negative 2 over root 29 squared plus 5 over root 29 squared. So that is going to give us, that is going to give us the square root of 4 over 29 plus 25 over 29, which is going to give us the square root of 29 over 29, which is going to give us the square root of 1, which is 1. And sure enough, our unit vector is only 1. The unit vectors 1, 0, and 0, 1 are called the standard unit vectors, and they're denoted by the letters I and J. These vectors can be used to represent any vector v as follows. So what we can do is take the components of v, v1 and v2, and really just turn them into scalars. And this is really representing the horizontal, and this is representing the vertical. So what we do is really get something that looks like, say, if we had, say, vector v being, 3, 5. Then our linear combination, right? Our linear, or this is in our component form, or maybe even standard form, but our linear combination with I and J would really just be taking those letters and making this 3I plus 5J. Nothing overly complicated here. But in order to do that, when we have, say, this example down below, first we need to figure out what is that component form. So for u, we have an initial point and a terminal point, and in order to find that component form, what we need to do is just really subtract. So remember, we're going to do terminal minus initial. So we're going to have negative 1 minus 2, comma, 3 minus negative 5, and that's going to give us, negative 3, 8. Okay, so that's our component form. So if we want to write this as a linear combination, what we're going to do is write this as negative 3i plus 8j. Now, if 8 was negative, we would put a minus sign there. All right. So in example 6, we're going to use that same u that we got, negative 3i plus 8j, and now we have v, which is 2i minus j, and we are going to find 2u minus 3v. So we're going to do some scalar multiplication here, but really this isn't any worse than it looked before. This is basically going to look like combining like terms. So 2u, that's really 2 times negative 3i plus 8j. If you want to go back to component form, certainly you can, but there's really no point. Minus 3 times, and that's 2i minus j. And this is just like algebra 1, right? We're going to get negative 6i plus 16j minus 6i. Just don't forget you're distributing a negative now. Plus 3j. And then we're going to combine our like terms. So our horizontal, these guys go together. So that's negative 12i. Right? And then we have 16 plus 3. That's 19j. Okay. And lastly, direction angles. So if u is a unit vector such that theta is the angle measured clockwise, from the positive x-axis to u, then the terminal point u lies on the unit circle, and you have u is equal to x comma y with cosine comma theta as my components there. And then if we were going to write this in linear combination form, we just pull the cosine and the sine out. So the theta here is going to be considered our direction angle of the vector. So we're going to suppose that u is a unit vector in the with the direction angle of theta. So if v is equal to ai plus bj, where a and b really are the components of v, this is going to be any vector that makes the angle theta with the positive x-axis. Then it has the same direction as u. So what we're looking at really here is, here's my x and my y-axis, right? And we have some vector on here. We'll put it in standard position. So here's my vector. The angle we're talking about is right here, this angle right here. And this is our vector v. Okay. So we can think of this as having our I here and our j here. Okay, or really we can write j, and I'm going to kind of change the color up so we can see it, here, and here's our I down here, and now we have this right triangle. So now that's where that cosine and that sine are coming into play, right? If v is going to be, or if u, actually, I guess we're using u as our unit vector, then we have a hypotenuse of 1, and when we go to do SOHCAHTOA here, that's where we're getting that cosine and sine coming into play. So then if we wanted to turn that unit vector into something else, all we're doing is going to multiply by the magnitude to fix that. So this is where we get this formula from. So for instance, if we have a vector of length 3, that's going to make an angle of 30 degrees with the positive x-axis. It's given by this formula. And really what's happening there is we're thinking of, okay, here is my, xy plane. Here's my 30-degree angle. Well, it looks more like 45, but whatever. If we have vector v, we're thinking about, okay, well, if this was for u, it would cut it off here. This is just a unit of 1, and we have I and j. But now we need to just make that triangle a bigger triangle. So now we have our new, our new I and j. Then we have our new I and j when we kind of make this longer by multiplying by the magnitude of v. It's just going to slightly change this problem. But the idea is we're basically just doing similar triangles. That's what it's coming down to. All right, so what we can do, because v is going to be equal to ai plus bj, and then it gives us this formula, what's going to happen is we can get our angle by doing the tangent. So we know that tangent is sine over cosine. So we can put in what we do know, and we're just putting that scalar in there to make our triangle longer. Okay, so our tangent is really just going to be whatever b is in our, v is really ab, right? So really our tangent is going to be b divided by a. So if I need to find the angle, I can do the tan inverse to find our angle. Okay. right, so what we're going to do is find the direction angle of each of these vectors. So really we have some random vector, 3i plus 3j. That's in a linear combination form. If you want to think component, that's just 3, 3, where this is my a and this is my b, but you could pull a and b from here as well, no problem. So if I want to find the angle, really I'm just saying that tangent of theta is going to equal 3 over 3, which means that tan of theta is equal to 1. And to be perfectly honest, we don't really have to do tan inverse. This should be one that we recognize. Our angle here should be 45, but if you need to do the inverse, you certainly can. You're going to get 45 degrees for that one. Another thing that's good to note is we should know what quadrant we're in, right? So if our component is, our components are 3, 3, 1, 2, 3, 1, 2, 3, that means our terminal, if our initial is on 0, should be at the point 3, 3, which means our angle is in the first quadrant, so 45 degrees makes sense. If we needed to be in radian, though it doesn't suggest that, you could do pi over 4, that would be fine. All right, let's take a look at the next one. So we have 3i minus 4j, that's my a and my b. Again, if you prefer to think of it this way, it means the same thing, doesn't matter. So that means that tangent of theta is going to equal negative 4 over 3. Definitely not one you would necessarily know off the top of your head. So what we would want to do is find the inverse of that answer. Let's see, negative 4/3. So when we do that, we're going to get kind of an estimated answer here. We're going to get... let's see. We're going to get about, sorry, I don't know why my calculator is not working for me. Give me just a second. Let's get that working. It should be like 53 something, or somewhere around that number. Let's see, we need tan inverse, and we need to be in degrees. Tan inverse of negative 4 divided by 3. Yep, oh, there we go. Okay, so we should get negative 53.1-ish, 1.3, something like that. Okay, so since that is our angle, we have to think about where does that put us, though, because we really do want to think about having positive angles here. So if we have our V, we're at 3, so 1, 2, 3, but negative 4, 1, 2, 3, 4. We're down here, and we want to be talking about the angle with the positive x-axis, so that would really be this angle in here. So we have our negative 53.13 degrees, or if we wanted to think of this kind of from the other direction, we could get the positive version of the angle as well.